Welcome back, everyone. In this video, we'll be going over the properties of definite integrals. And I'm going to go ahead as we go through and just write the formulas down or the words down. But for definite integrals, because we don't have actual formulas, we're thinking about everything in terms of areas in this area that can sort of be negative. I wanted to make sure you kind of talk about it as we write them down. So with that in mind, we'll go ahead and go through all the properties that I'm going to state here. Now, the first one here says continuity. This is actually more so about a necessary property. It says if your function f is continuous. Actually, I have to add in a little extra thing because we only care if it's continuous from A to B. It doesn't have to be continuous everywhere. So if it's continuous on A to B, then f can be integrated, that definite integral, on A to B. Right. So if you kind of want to make sense of that, all you really have to do is think about it this way. If I'm representing an area, let's say from A to B, which is what the definite integral does, if I'm not continuous, then the idea of area is very weird. So let's say my function starts here and it goes up to here about halfway, but then all of a sudden I have an open circle down here and it just kind of does this. Well, in theory, what it's kind of, you might guess is that, well, I would just add this area up and then I would add this area up. Well, the problem is the open circle here. Actually, there's more than one problem, but the easiest problem is that there's an open circle here. It's a hole. And because there's an open circle, you can't actually find the area because this isn't actually a bound. Whatever this number is, let's say it's just called C, you have to be able to plug in C. And we can't because when we plug in C, we actually get this value up here where the closed circle is. So a necessary thing is that you must have a continuous function. If you do not have a continuous function, there can be workarounds. But at this point, we just want to make sure that our function's continuous. All right, now the next couple are going to look very familiar, especially when you compare it to the rules of derivatives, the rules of antiderivatives, constant multiple. So all this means is that if you try to integrate a function f of x from A to B by some number k, so k is just a number, you use a different color to highlight that, then what you're allowed to do is exactly like we did with derivatives and antiderivatives, you can bring it outside or just kind of leave it there. And we're allowed to bring numbers outside. So A to B of f of x dx. So you can kind of come up with examples of why these work, but these are properties that we just really want to know. If you think about it being 2, maybe your function is a flat line, so you get a rectangle with a certain height. If you're doubling your function, so let's pretend f of x is 1, so this is a rectangle with height 1. Well, if your k is 2, then really we just have the same exact base of the rectangle, but with double height. So we're multiplying the area by 2. Right, so, once again, you don't have to go through the proofs of these or anything. They're kind of hard to prove. But if you think about them in terms of area, they make a lot more sense. The addition and subtraction property, that's pretty much the same thing that we had with derivatives and antiderivatives as well. It's that if you're adding or subtracting two functions together, some people like to put brackets or parentheses around these, but whatever's in between the integral sign and the dx that's what you're quote unquote integrating, so finding the area of. You can split it up. So it's the same thing as the integral from A to B of f of x dx, and then plus or minus, depending on whether you have a plus or minus here, A to B of f of x. Sorry, that should be g of x, because the second one's g of x dx. All right, so just keep that in mind going forward, is that these two are pretty much saying the same thing as derivatives. If you want to compute an integral, you can leave numbers alone. If you want to compute an integral that having an addition or subtraction, you can break it up over addition and subtraction. Right? So really the point is same kind of rules as derivatives. It's just that we're doing something different here. We're not doing the derivative. So one thing that could happen I described before is that if you integrate and you actually have the bigger number on the bottom. So, you know, we aren't specifying here, but pretend A is 0 and B is 1. So the bigger number's on the bottom and you just don't like that. You might not like it because what does it mean to do the area from 1 to 0? That's kind of going backwards. Well, what happens is if you reverse the order of integration, so that means you put the bottom on the top and the top on the bottom of your function, you just need to keep a negative sign there to keep it balanced. So just think of it as a negative sign to flip the integral bounds or limits. So you just need a negative sign to be able to flip the limits or the bounds, whichever one you call them. So just keep that in mind. It's very, very useful property because it's really hard to understand if you're trying to understand area. What does it mean to integrate from 1 to 0? Because that's going backwards. In math, we go from left to right. This would tell us to go from right to left. Right. And I think one of the most interesting properties is this. If you're integrating, but the top and bottom is the same number, what do you think that is? Well, if you think about it in terms of area, what you should do is come up with the number 0. And the reason is because when you're integrating from one number to itself, we can just use a here. It doesn't matter what the function looks like, so let's just say this is y equals f of x. What we're trying to do is find the area of the thing that's starting at x equals a, but also ending at x equals a. And really what we're doing is trying to find the area of something, but its width or the length of the base is 0. So if you think back to when we talked about the Riemann sums and the approximations with rectangles with the left and right, all those b minus a over n's would be just 0. So you're multiplying a whole bunch of things by 0, you get 0. But that's a pretty important property. Surprisingly, does it come up a lot? Not necessarily, but when it comes up, you just want to know that if the top and bottom are the same, it gets 0. It doesn't matter what the inside is. All right, so the last two here, these are the last two, not only because I ran out of room and I put them over here, but they are pretty important properties as well. They're sort of related more so to the last two here. If you have to integrate from a to b of f of x dx, and then you also want to integrate from b to c of f of x dx. So this is finding the area from x equals a to x equals b. This is finding the area from x equals b to x equals c. Well, that would be the area from x equals a to x equals c of your function. Okay. And you can kind of think about it in terms of, let's say a is here and b is here and c is here. And we'll draw just f of x being up here. The reason why this makes sense is, well, this first integral here, this is the area from a to b, so this would be like this one. And then the second one from b to c would be this area. And then what's the last one saying? This is saying find the area from all the way from a to b. Well, that would just be adding these two areas together. So that's exactly what this says. If you add this area together and this area together, you get the entire area. And don't worry, we'll practice, for the most part, we'll see these first two rules all the time going forward, but we'll practice especially the reverse order of integration and these last two rules very, very soon. All right, so the last one is with subtraction. So if you have a to b, actually, let me use c here because I want to try to use the same picture. A to c of f of x dx minus b to c of f of x dx. Well, this actually equals the integral from a to b of f of x dx. Now, because all these areas represent just numbers, they're just pretty much areas, you can actually add this over to this side and get this same equation back. But when you see subtraction in a problem, if you have something set up like this, it's not really easy to think about that. But what this is saying is that this, we want to find the area from A to C, so the entire thing, the entire area, both parts. But when we subtract off the area from B to C, well, we're subtracting off the green area here. So if we want to find the whole area, but then take off this area, what area are we left finding with? We're left finding the red area, which is exactly this, from the A to B. Both of these are the same. Okay, and once again, we'll see all of these in action very soon, but I just wanted to go through and show you these and kind of where they come from. They are pretty much all the basic properties of integrals. We'll eventually have a lot of formulas for integrals when we have certain functions like sine and e to the x and everything. But these are very important properties of integrals. Now, just like with derivatives, when it comes to integrals, if you don't have a rule for it, don't try to use one. So something that's not true. I'm just going to give you the two primary examples here. If you try to multiply, so let's say you have the integral from a to b of f of x dx and the integral from a to b of a different function g of x dx, this does not equal the integral from a to b of f of x times g of x dx, right? And that's just because you're trying to multiply an area by another. If they're completely separate things, then they don't need to equal at all. Right? Think about it as if you have an area of a circle and an area of a square and you multiply them. Well, what is that really getting you? If you have the area of a circle and an area of a square, when you multiply these areas, that doesn't mean anything. So just remember, you don't have a rule for multiplication because there's not one. And then the other rule that's easy to mess up, you're allowed to bring out numbers. So anything without x, but anything with x, you have to keep in the integral. So something like, you could literally be anything with x. I could have e to the x times f of x dx. Because this has an x on it, it has to stay inside. This does not equal e to the x times the integral from a to b of f of x dx. And so everything with an x on it must stay inside. And these are pretty much the most iconic rules, but you can come up with, division doesn't work. So if you do f of x divided by g of x, you cannot divide them inside. You can come up with any function here, sine of x. You could have just x, but anything with x at all, this is not true. All right, so we're going to use some of our properties above just to practice them to do this first problem here. All right, and the directions here says use the properties of definite integrals to write the following as a single integral of the form a to b of f of x dx. So this is the problem here. I hand wrote it just to make it a little bit bigger because sometimes these are small when you write them in the math way. We have to integrate from -4 to 2, then from 2 to 3, and then from -3 to -4 of the same function. Now, when you're integrating the same function on different bounds, you want to think to these two rules. We want to consolidate them into one integral. And that's really what it wants to get me at. So I kind of added this part in here to say, this is going to equal the integral from fx dx. We just need to figure out what goes on the top and bottom. Where does this start and where does this end? Well, the way I like to do this is actually kind of using in words, but also a number line, because we have areas. So this first integral, what is this asking us to do? It's asking us to do the area from -4 to 2. So I'm finding the area of this thing. And what's the next part asking me to do? It's asking me to do the area from 2 to 3. So from 2 to 3, I'm doing that area. So at this point, if I just combine these two together, I would have -4 to 3, because I would be starting at -4 and going to 3. All right, what about the last one here? Well, there's kind of one thing I want to fix first. And the thing I want to fix is that if you look at your bounds, the bigger number is actually on the bottom. The smaller number, -4, is on the top. The bigger number is on the bottom. And this is really hard to understand in terms of area. So since the bigger number is on the bottom, flip and change the plus that's in front here to a minus. All right, so pretty much what we're doing is this rule here. We want to flip the order of integration. We want to make the smaller number on the bottom. Right now, the bigger number is on the bottom because -3 is bigger than -4. And when we do that, we have to make up for it by adding a minus sign here. Since there's a plus there, the easier way to think about that is making it a minus. All right, so I'm going to go ahead and just do that down here. Now I have -4 to 2 of f of x dx. The first two are fine, and we're not going to make any adjustments to those. These smaller numbers on the bottom for both, but now this is a minus, and we have -4 to -3 of f of x dx. All right, now if you think about minusing an integral as taking the area away, what we have here is we discovered these two parts. We want to find the area from -4 to 3, but this says because of the minus, don't count the area from x equals -4 to x equals -3. So from -4, where our original one's starting, up to -3, let's pretend it's right there. We're not doing this area. Well, that means our final answer here, what we are doing the area of is from -3 to 3, because we had -4 to 3 from the first two, and we took off -4 to -3. So the final area we're finding is from x equals -3 to x equals 3. Right, and the way we use that in our integral is the smaller number goes on the bottom, -3. The top number gets the bigger number, which is the +3. Now that's all we're filling out here, but if you don't make that adjustment, that can be pretty hard. And thinking about this in terms of areas is very helpful. Now the next one, this one's probably a little bit easier as far as properties go, because it's more like the derivative property. It says the following. If f of x, the integral from 0 to 5 f of x dx is equal to 31, and the integral from 0 to 5 f of g of x dx is equal to 16, we want to find the integral from 0 to 5 of 2 f of x times 3, or minus 3 times g of x. Well, since that's what we want to find, that's what I'm going to start with writing. We have 2 f of x minus 3 g of x. Right, now remember way back when we started doing derivatives and derivative rules and all that stuff, we had to break down into what we know. We only know the answer or how to get this number if only f of x or only g of x is inside. Which means if you think about what we have here, if we had just this f of x, then we could know the answer is 31. If we had just this g of x, we know the answer is 16. Well, you have rules that allow you to split up an integral. The first thing here is split it up over the minus. So we have 0 to 5 of 2 times f of x dx minus the integral from 0 to 5 of 3 times g of x dx. Right, and that's exactly what it looks like. If we're adding or subtracting inside, we split it up and make two integrals. So this is exactly our addition or subtraction rule with subtraction. Notice that when I integrated, both the limits stayed the same and we put a dx on each. So you have to make sure you do that. We're going from 0 to 5, so each one goes from 0 to 5. Both have a dx. Now the only other thing you have to do before you can finish this is this -2 and -3 are the problems, because if they were outside, now we could just plug in the numbers. But luckily our integral rule says we can move numbers out front, and that's supposed to be a 3 because that says 3. We can move these numbers out front free of charge. That is our other property that was the constant multiple property. there. So we can move numbers because they don't have x on them out of the integral free of charge. And when we do that, we have 2 times the integral from 0 to 5 of f of x dx minus 3 times the integral from 0 to 5 of g of x dx. And now the main thing is we now can plug in because we know what this is. This is 31. We know what this is because this is 16. And when we plug them in, what do we get? We get 2 times 31 minus 3 times 16. This is 62 minus 3 times 16 is 48, and 62 minus 48 is 14. Now, when it comes to properties of integrals, they are used pretty often. The ones that we use here in the second, like splitting it up, bringing numbers out, that's what we'll use more often. But it is important to at least understand how to deal with something like this. If you have to do 10 integrals, but they're all the same function and their bounds are just different, then you can consolidate it to one integral. And that's a lot easier to do. All right, so what we'll do in the next video is just finish up this section by pretty much going back to the first problem where we had a graph that we were given, we had some shapes in it, and we used geometry to evaluate the area. So we're going to do the same thing, but starting with formulas. I'll see you there.